All right, let's do some practice. So here we're going to go through and walk through spring 2022. Keep a few things in mind. First off, this exam has 5 problems. Now, the exam that you'll be having is a little different. It has 6 problems, so you get 1 extra problem. Or, as you know, your instructors like to say, 1 more unit of fun, because aren't problems fun? Also, the problems you have will be slightly more tuned in to what we've been doing. So they'll be more in line with what you've seen, for example, on the quizzes. Well, this means it might be easier, it might be simpler, it just depends. But at any rate, let's begin. The first problem. Use the Laplace transform table to find the Laplace transform of f of t, which is u of t minus 1, e to the 3t plus 2t, where u is the unit step function. In this exam, they use a very fancy u. But all right, now, of course, they say the table, because everything for the Laplace transform works from the table. We almost never use the definition. All right, we see a unit step function. And so when we look up our table, we have the following, namely that the Laplace transform of u of t minus a, and I'll say g of t minus a is equal to e to the minus as and g of s. All right, so that's our basic rule. So what does that mean? Well, see how there's a t minus 1 here? To use this rule, we need to make what's attached to it, in this case, e to the 3t plus 1, look like something involving t minus 1. So that's actually the first step. Oftentimes, most of the work in these Laplace transform problems is in rewriting the expression to be something that we can actually use. That's it. It really comes down to that. It comes down to saying, are you comfortable with the table? And can you say, okay, let me take what I have and make it fit what's on the table? If you can do those 2 things, usually these aren't bad. Okay, so here's what we're going to do. We have our u of t minus 1. Now here, we're saying, all right, we're going to use a simple trick, which is, hey, if it's not on t minus 1 yet, I'll make it like t minus 1. So that's e3, and I'm going to write t minus 1 plus 1, right? Because t minus 1 plus 1 is just another way of saying t, and then plus 2 times t minus 1 plus 1. All right, so this is u of t minus 1 times, now here, this will be e 3 times t minus 1, and then we'll have this 3 multiplies through. Yeah, so we have a plus 3 upstairs, and so that can become multiplication, and since it's a constant, I'll write in front. And then I'll distribute through 2 t minus 1 and 2. All right, now we're ready to go. And what happens here? Well, we have, this is our u of t minus a, here's our g of t minus a. So the e cubed, well, that's going to go to e cubed. This e to the 3t minus 1, in our minds, we're like, oh, treat it like e to the 3t. So this is going to go to 1 over s minus 3 plus 2. Now t minus 1, again, in our minds, we think of it as t. So that's going to go to 1 over s squared. And then the 2, okay, that comes 2. Really, it's 2 times 1. And 1 goes to 1 over s. And this u of t minus 1 becomes e minus s. And that's it. We're done. Now, we could rewrite it. In this case, I don't think it really helps us any. And so there we go. That wasn't so bad. Wow, we're going to do great Well, yeah, that's the plan, right? You don't walk into a test saying, I'm going to do not great. So, okay, let's move this up. Find the inverse Laplace transform of 6e to the minus s over s squared minus 9. Now, if you were really good at memorizing things, you might say, whoa, this looks suspiciously like the sinh function. And we'd be like, yes, you have good taste. But most people aren't good at memorizing things that we don't leave on the table. Now, you might say, wait, sinh, what's the sinh function? Well, that's e to the minus s, e to the s plus e to the minus s. Sorry, I can do this. I've done this before. Sinh is e to the s minus e to the minus s over 2. But that's a different story. Okay, so we're actually going to do what we have on our table, which doesn't involve sinh. But we say, look, there's polynomial over polynomial. We think partial fractions. We anticipate partial fractions. We see this e to the minus s. We say, look, e to the minus s is not polynomial. So we move it to the side. And then we say downstairs factors s minus 3, s plus 3. Okay, so we're going to do partial fractions on this part without the e to the minus s. Then when we're ready, we'll throw the e to the minus s back. So 6 over s minus 3, s plus 3. Well, it's something over s minus 3 plus something over s plus 3. We clear our denominators. So multiply everything by s minus 3, s plus 3. And we get to the place where 6 is equal to a times s plus 3 plus b times s minus 3. And at this point, we say, all right, make good choices. If we choose s equals 3, we get that 6 equals 6a, right? So that says, oh, a should be 1. If we set s equals negative 3, well, that will be 6 equals minus 6b. So b equals minus 1. So the punchline is that this expression can also be written as 1, which is a, over s minus 3, plus b, which is a minus 1, over s plus 3, and that's e minus s. Now, we get the following. Pieces, we go through this one piece at a time. 1 over s minus 3 normally goes to e to the 3t, so we're going to write that down. Then we have s plus 3 would normally go e minus 3t. And then we have this e minus s. Now, what does this do? Well, this says shift by 1. So in other words, t is going to go to t minus 1, and we're going to get a u of t minus 1 in the answer. So our final answer is the following. E 3 t minus 1 subtract e minus 3 t minus 1, and all that times u of t minus 1. And done. That's it. That's the answer. Wow. Cool. So that's not so bad. Yeah. But, okay, pro tip. Remember, partial fractions, you need polynomial to polynomial. So if you have these e to the minus, something s, pull it to the side and do partial fractions without it. All right. Good. Well, one problem down. For the second problem, solve the initial value problem using Laplace transforms. And we look at this initial value problem and think, what should we do to solve it? Let's use Laplace transforms. Well, yeah, because it tells us to, right? And, we're very good. We've learned our lessons. If we want full points, we follow the instructions, right? Of course. And we want full points. We want all the points. And nothing too surprising going on here. So we say, okay, we're going to take the Laplace transform, and we get the following. The Laplace transform of x double prime minus the Laplace transform of x prime minus 6 Laplace transform of x equals the Laplace transform of 0. Now, x double prime, on our sheet, we see this becomes s squared capital X, subtract s times x of 0, which is 2, subtract x prime of 0, which is 1, minus parenthesis. Now, this parenthesis is important because it'll make sure we understand the minus distributes through. So x prime would go to s times capital X, subtract x of 0, which is 2. Subtract 6, and just out of habit, parentheses, and Laplace transform of 0 is 0. Now, so we've taken the Laplace transform. That's the first step. Step 2, solve for x. Well, all right, we see s squared x, sx, 6x, so we just gather s squared minus s minus 6 times x. And you will see, that looks amazingly like the original differential equation. Not a coincidence. It should. If it doesn't, oops, fix it. All right. Now, on the other side, we'll have what? Well, this is a minus 2s comes across as a plus 2s. And let's see. Let's be careful here. Remember that we said this minus distributes because we put a parenthesis there. So this is really a plus 2 and a minus 1. So plus 2 minus 1 makes a plus 1 on the left. To the right, minus 1. All right. And, well, while we're here, we peek at this and say, does this factor? Now, generally speaking, yes. In fact, if you see a minus here, it pretty much is a guaranteed it's going to factor. Might not factor nicely, but it's going to factor. Now, in this case, we need two numbers that multiply together to give minus 6 and add together to give minus 1. So two such numbers are minus 3 and plus 2. All right, we can check s squared, 2s minus 3s, minus s, minus 6. All right, well, that gets us to the following. X is equal to 2s minus 1 divided by s minus 3, s plus 2. Okay, well, at this stage, we've solved for x, and now we're preparing to take the inverse Laplace transform, which comes down to rewriting. And yet again, partial fractions are coming in. We should anticipate partial fractions will frequently show up. All right, well, not on every problem, but on a non-trivial number of them. So 2s minus 1 over s minus 3 times s plus 2. Well, that's something over s minus 3 plus something over s plus 2. Again, clear the denominators. So you multiply by the original. And, well, when we do that, we get 2s minus 1 is equal to a times s plus 2 plus b times s minus 3. Now, make good choices. Well, one good choice is we can choose s equals 3. If we do that, we'll have 6 minus 1, which is 5, equals a, 3 plus 2, which is 5, so 5a, and 0b. So a equals 1. How about negative 2? We're going to get minus 4 minus 1, which is negative 5, 0, minus 2 minus 3, is negative 5. Oh, so b equals minus 1. Don't always assume we're going to get plus 1 and minus 1. I think they chose it so it worked out this particular time, but it might not do that on your test. So just be ready. Just be ready. Okay. Now, where are we at? Well, that tells us that capital X looks like 1 over s minus 3 subtract 1 over s plus 2. Okay. Well, wait. Minus 5 equals minus 5b. That means b is plus 1. So this is a plus. Sorry about that. Yep. No matter how often you do these kinds of problems, small mistakes can creep in. So it's good to double check and say, like, is this going to work? And, all right, so let's finish it up. Inverse Laplace, that says the inverse Laplace of 1 over s minus 3 would be e to the 3t. And here, inverse Laplace of 1 over s plus 2, this is really s minus minus 2. So this is e minus 2t. Now, one thing you can do as a sanity check is check your initial conditions. When you plug in 0, do you get 2? Well, you get 1 plus 1. Now, if you're wondering, how did I catch that minus? I was kind of looking ahead and saying, wait, I'm not going to get 2. What? And so I was like, oh. So then I started looking for mistakes. And so, checks are useful. If you take the derivative, we should get 1. Well, here you get a 3 come down, here you get a minus 2 come down, and 3 minus 2 is 1. So we satisfy the initial conditions. That's a very good sign that we did it right. Oh, good. 2 down. For number 3, use Laplace transforms to solve the following non-homogeneous ODE. X double prime minus 10x prime plus 34x is equal to 3 e to the 5t. And x of 0 equals x prime of 0 equals 0. And it says, hint, you can leave your answer in terms of a convolution. That's not really a hint. It just says, if you're feeling lazy. So we'll do it both ways. How's that? Both as a convolution and as a not a convolution. So let's remind ourselves of convolution really quickly. So convolution is the following. It would be the integral 0 to t of f of tau, g of t minus tau, d tau. So that's what we mean by convolution, and the shorthand is f star g. Now, why do we like convolutions? Well, turns out the Laplace of f star g is equal to f g. In other words, convolution becomes multiplication. But it also can be written as, if I'm taking the inverse Laplace of a product, that's a convolution. So when it says you can leave your answer in terms of a convolution, it says, if you get down to a product of things, then just convolute the inverse Laplace of the pieces. All right. So that's that little side note. Okay, so we proceed like we would any problem involving differential equations and Laplace transforms. We take the Laplace transforms of both sides. So Laplace transform of x double prime minus 10 Laplace transform of x prime plus 34 times the Laplace transform of x is equal to, I'm going to run out of space here. All right, we'll go to the next line, 3 Laplace transform of e to the 5t. There we go. All right, now we have our initial conditions are both 0. Whew, that makes it easier for us. Well, what does that say? Well, that says the Laplace transform of x double prime is s squared x subtract 0, subtract 0. All right, great. Minus 10, the Laplace transform of x prime would be sx subtract 0. Plus 34, Laplace transform of x is x equals, here we have 3 times 1 over s minus 5. All right, or s squared minus 10 plus 34 times capital X is equal to 3 times 1 over s minus 5. All right, now let's talk about s squared minus 10s plus 34. Does it factor? It's not looking very promising because there's not a lot of ways to write 34. It turns out it's either 1 times 34, hard to get to 10, or 2 times 17, still hard to get to 10. Okay, so it doesn't factor nicely. So when it doesn't factor, what do? Well, we complete the square. So this would become s squared minus, whoops, I forgot my s there. I'm sorry about that. S squared minus 10s. Now to complete, take that middle coefficient, minus 10. And by the way, oftentimes I skip a step with complete the square, but since we're together, it's me and you, I'm just going to remind us, when you do this for complete the square, make sure this is a 1. If it's not a 1, fix it. Okay, so it's a 1. All right, take the middle term, divide by 2, negative 5, square it, add 25. So that would make a perfect square, but I need to get to 34, and so I need to add enough to get back up to 34. So this is s minus 5 squared plus 3 squared. All right, so that gets us to x is equal to 3 times 1 over s minus 5 times 1 over s minus 5 squared plus 3 squared. But actually, this looks a lot like sine. Now, the s minus 5 means there's a shift, which means an exponential function of e to the 5. But you can say, look, okay, hey, this is the same as 1 over s minus 5 times 3 over s minus 5 squared plus 3 squared. All right, so what are the rules we're going to be using to take our inverse Laplace here? Well, because they said you can leave your answer in terms of a convolution, we say, oh, I have a product. That's my FG. So here's my F, and here's my G. So now I just need to figure out what happens individually. Well, 1 over s minus 5, that's pretty simple. That would be e to the 5t. What about 3 over s minus 5 squared plus 3 squared? Well, there's two rules being combined. So the rules that are being combined, let's see if we can probably fit it down here in this corner, is if you take the Laplace of sine of bt, that's equal to b over s squared plus b squared. So you'll see, s squared plus b squared, b on top. And I say, well, wait a second, what about the s minus 5? Well, whenever you see a shift inside, that uses the other rule, namely the Laplace of e to the ct f of t is equal to f of s minus c. So what that tells us is when we see an s minus 5, it says, oh, we shifted. Now in this case, because it's s minus 5, that means we're going to have an e to the 5t, right, because that's our shift. And then we think of it as without the shift to be 3 over s squared plus 3 squared, which says, oh, that would be sine of 3t. All right, now I'm going to actually do something which is anticipating what's about to come. So one of these should be f, one should be g. It doesn't really matter which one is which. And because one of them is going to have a tau, one of them is going to have a t minus tau, I want this one to have the t minus tau. So let's just change names just for a second. Because it doesn't really matter, does it? All right, so if we apply the hint, which is really, again, it's not a hint, it's just saying all those who are just not in the mood to do, our partial fractions. And I'm just like, who wouldn't be in the mood to do partial fractions? I mean, we love partial fractions. That's cray that we would not want to do partial fractions. But, all right, so little x of t, we can say is the convolution e to the 5t sine of 3t with e to the 5t. Now, they wouldn't be happy if we left it like that. We really want to make sure, like, hold on, do you really know convolution? All right, we want to get it to this integral form. Okay, so that would be the integral 0 to t of e to the 5 tau sine of 3 tau times e to the 5 t minus tau. I can do that. D tau. All right, good. Did we make it? All right. Now, and there we go. That's our answer. But could we do better? Well, we can, right? We can do better. Notice a couple of things happening here. So you have, this is e to the 5t, and then we subtract 5 tau. What does that tell us? If you have e to the 5t, subtract 5 tau, and here's e to the 5 tau, that becomes equal to integral 0 to t of e to the 5t, because the 5 taus cancel, sine of 3 tau. Okay, great. But now, like, integration by parts, I don't like that. Or is it? It's not. Okay, check this out. Check this out. E to the 5t is what? I know that's a very vague question. Let me refine. In relation to this integral, what is it? It's a constant. Right, exactly. Comes out. All right, good. So, let me go grab another piece of paper here because we're running out of space. And, all right, so grabbed a piece of paper here, and we'll just copy this over. So we are up to the following. This is equal to, the e to the 5t came out, integral 0 to t of sine 3 tau d tau. Oh, great. Well, what's that? Well, you can compute that integral. Because the integral of sine is, did you say cosine or negative cosine? Which one? It's negative cosine. Yeah, it's one of those weird ones. Wait, which one is it? Yeah. So negative, because of the 3, 1/3 cosine 3 tau. Evaluate that from tau equals 0 to tau equals t. And what we end up with is e to the 5t minus 1/3 cosine 3t, subtract, plug in 0, you get minus 1/3, which actually becomes plus 1/3. Or we can write this as, this is 1/3 e to the 5t, subtract 1/3 e to the 5t cosine of 3t. Now you're thinking, would we have to have gone all that way? The answer is no. Because of the hint, we could have stopped back here. And I'm just like, but why would we stop when we can keep going? Now, you might be saying, okay, well, that's cool, but what if I was in the mood for partial fractions? You're a person after my own heart. We would get along magnificently. So let's try that. Let's do some partial fractions. So what do we have? I'm going to jump back and just point out, we have to do partial fractions to this. So I'm just going to start at that point. So we have 3 over s minus 5. And I'm going to leave this as s squared minus 10s plus 34 for the moment. So that becomes a over s minus 5 plus b over s squared minus 10s plus 34. All right. We'll make some notes. So this part is this if we want to do partial fractions. All right. Well, I made a mistake. Because this is quadratic downstairs, it doesn't factor. It's not b. What is it? It's bs plus c. Now, a simple check. Whatever the degree is on your starting has to be the number of things to solve for. So it's really degree 3, so I have to have 3 constants to solve for. All right, clear denominators. Whew. Okay, so when we do this, we're going to get 3 is equal to a times s squared minus 10s plus 34 plus bs plus c times s minus 5. Now we could plug in 5 and see what we get, but how about we just expand and group coefficients? Let's see what happens if we do that. Well, we're going to get, for s squared, we're going to get a plus b s squared. And then for s, we're going to get a minus 10a. Here we'll get minus 5b. And here we'll get a plus c. Now for our constants, we're going to get a 34a and a minus 5c. All right. So comparing coefficients, a plus b needs to equal 0. Minus 10a minus 5b plus c needs to equal 0. And 34a minus 5c has to equal 3, right? Because there's a 3 over there. Okay, well, what do we have? We have 3 equations and 3 unknowns. And you're like, I preferred this convolution, Steve. I know. Sometimes it looks fancy, but, we should see both ways. All right, what can we do? Well, one thing we can do is for the first equation, a plus b equals 0. Well, that's really simple. That tells us that b equals negative a. So if we come here, we say, okay, if b equals negative a, this is minus 10a, and then minus 5b becomes plus 5a, plus c equals 0. So we can say, okay, that says minus 5a plus c equals 0, or c is equal to whatever. Take a times 5. Yes? All right. So we get the following. We have 34a subtract 5 times 5 makes 25a. That has to equal 3. Well, 34 subtract 25 makes 9a. So we say, aha, a equals 1/3. Now we work our way back. All right, c has to be 5/3. Great. And b has to be negative 1/3. So we solve for our coefficients. Okay, so we have the following. When we put this together, we have that our capital X is equal to a is a 1/3, so I'm going to write this as 1/3, 1 over s minus 5. And then we're going to have a b times s plus c. Now, notice I have a b is a minus 1/3, so I'm going to go ahead and pull out a minus 1/3 as well. So that says then b, the rest of b would be 1, and then here, c, because I pulled out a minus 1/3, because I'm pulling it out, right? that would make it a minus 5. So we'd have s minus 5 upstairs. Now we put in, hey, we know what the complete the square does. That's s minus 5 squared, and then plus 3 squared. And now we're saying, great, that tells us our answer, because that's going to say that our answer is 1/3. 1 over s minus 5 becomes e to the 5t minus 1/3. Now, because we see s minus 5, they're both the same. It's already in the right form. We have a shift, e to the 5t. And then s over s squared plus 3 squared makes cosine of 3t. And lo and behold, they're the same. Is that a coincidence? No. No, it's not. It should be the same, because we should get a consistent answer. But, it's nice to know we have choices. Ah, what a fun problem. Now, I know if you're watching this, you're like, but it took so long. Well, yeah, because we did it twice. This is the problem that's so nice. Don't worry, we won't do it thrice. But that was fun. All right, we're at the halfway point. Time to start heading down. On number 4, solve the following initial value problem by using the Laplace transform. Y double prime plus 4y prime plus 5y is delta of t minus 2 pi. Y of 0 equals 1. Y prime of 0 equals 2. And as a reminder, I know it says remainder, typo. Typos happen on test. Delta is a Dirac delta function. So remember, that's our little pulse, right? So really, it doesn't say this in the problem, but it says, oh, this is essentially like a differential equation that you see in a spring mass system. And if we wanted to, we could create a whole story. It's like, oh, we have a spring constant of 5, a mass of 1. We have a damper going in there with a damping constant of 4. And, we have some initial conditions. And then at 2 pi, we whack it with a small hammer. And, but we don't have to. We just have to solve it. All right, so we start. We take the Laplace transform of both sides. So the Laplace transform of y double prime plus 4 Laplace transform of y plus 5 Laplace transform y prime plus 5 Laplace transform of y is equal to the Laplace transform of delta t minus 2 pi. Now, looking ahead, whenever our differential equation involves delta, our answer has to involve u. Because the delta says, I do something at a particular system, and that says, I'm going to turn on some resulting behavior that was the cause of that. Okay, so our final answer has to involve a u of t minus 2 pi. Just remember that. It'll come up naturally, right? But, okay, so what do we have? Well, we're going to get s squared capital Y minus s times 1 minus 2 plus 4. Notice the parentheses. Make sure we distribute things appropriately. S capital Y minus 1 plus 5 capital Y equals, and here it's e to the minus 2 pi s. Okay, well, we now solve for y. So we group s squared plus 4s plus 5 capital Y is equal to, well, the s will come across. Here we have a minus 2. Here we have a minus 4, right? Because the 4 distributes through, which would make it a grand total of minus 6. So it's going to come across as a plus 6. And we don't forget we have an e to the minus 2 pi s. All right. Well, before we do much else, we'll take that s squared plus 4s plus 5 and we'll do some completing the square. Of course, we sort of like, does it factor? Yeah, it doesn't factor. So this becomes s plus 2 squared, because plus 1 squared, if you work it through. Well, okay, you can sort of do it mentally, but if you need to do it slowly, it's s squared plus 4s. Okay, 4 divided by 2 is 2. 2 squared is 4, so I need to add 4. But there's 5, so there's a plus 1. So that's where you get your plus 1 squared. And then that rest of it becomes s plus 2 squared. All right. Now you're probably thinking like, cool, let's divide over. But we know how these things work. We say, oh, I see this s plus 6 here. Now, what do I want? Well, I want to make it look like an s plus 2. And you're probably thinking, well, how do you make s plus 6 look like s plus 2? And the answer is, you write it as s plus 2 plus 4. Now, you might be saying to yourselves, why are you doing that? Well, we can anticipate what is going to happen. Because when we divide, we're going to have this s plus 2 quantity squared plus 1 squared, which means that the numerator, we want to make it look like s plus 2. So, in particular, we get that capital Y is s plus 2 over s plus 2 squared plus 1 squared plus 4 times 1 over s plus 2 squared plus 1 squared plus 1 over s plus 2 squared plus 1 squared e to the minus 2 pi s. Now you might have said, well, Steve, we could have just done that with partial fractions, right? Take s plus 6 over s plus 2 squared plus 1 squared and done partial fractions. And the answer is no, partial fractions won't do anything. You run partial fractions, it says, yep, I'm happy with what you have. Go with it. And so mostly it's just a matter of saying, hey, I know I need to make, whenever I have shifts going on, I need to make my upstairs match my downstairs. All right, well, what to do? Well, the answer is we're basically done. Okay, so if you've been practicing and paying attention, we see the s plus 2. That tells us, e to the minus 2t. There's a shift. And then we say, the rest of it looks like s over s squared plus 1 squared. Say, well, that is cosine t. And then we say, okay, then there's a 4, 1 over s plus 2 squared plus 1 squared. Again, the s plus 2 squared tells us e to the minus 2t, and 1 over s squared plus 1 squared, because now we say, okay, we've accounted for the shift. That looks like sine of t. In particular, we're in luck, 1 and 1. And then we say, okay, well, what about this last part here? Well, okay, here we got to be a little bit careful, right? Because this part by itself would go to e to the minus 2t sine t, because it's right there. But this says shift by 2 pi. So what we're going to get is e to minus 2 t minus 2 pi sine of t minus 2 pi, and then u of t minus 2 pi. And that'll be the answer. In fact, that's perfectly great as an answer. Of course, we can clean up just a smidgen. Say, look, this is really sine of t. And so our final answer will be e to the minus 2t. In fact, what could we do? Notice this part here. This is e to the minus 2t. Then we have minus 2 pi. That's e to the 4 pi. So you could factor e to the minus 2t out if you wanted to. You don't have to. And you can write this as cosine of t plus 4 times sine of t. And then plus e to the 4 pi sine of t u of t minus 2 pi. And there we go. That's it. That's the answer. Now, of course, we can do a couple of sanity checks and say, all right, what is this the right answer, right? Well, when you plug in y of 0, do you get 1? Well, this is 1. That's 1, 0, and that's been turned off. It hasn't turned on yet. So that is 1. Well, y prime is 0. Well, it's a little bit tricky, right? Because you actually have to do a product rule. So you'd have negative 2t, and the rest would be the same, which would be a total contribution of negative 2. Or here you have a 1, and then this would go, negative sign goes away. 4 cosine makes a 4. And that has been turned off, hasn't gone on yet. So we get a contribution of 4. Negative 2 plus 4 is indeed 2. So we do match the initial condition. So nice, nice. And cool. And of course we could do some other small things, but really this is about as nice as we can hope for. All right, good. Well, almost there. The last problem on this practice one. Now, keep in mind, as I've mentioned before, this test has 5, but the next one is going to have 6. So be ready to do 6 problems and pace yourself appropriately. Consider the initial value problem. Y double prime plus x minus 1y is equal to 0. And y of 0 equals 1. Y prime of 0 also equals 1. And a solution in terms of power series y of x is the sum from 0 to infinity, some unknown coefficient Cn, x to the n. Find the first 5 coefficients, C0, C1, C2, C3, C4, of the power series expansion of y of x. Now it says find 5. 2 of them are freebies. Now you might say, wait, they're freebies? How? Where? What? Well, because initial conditions are really saying, how do you start your series? So as a reminder, y of 0 is C0, and y prime of 0 is C1. So even if that's all we wrote down for this problem, we'd get a couple of points. Like, wow, that's it? Just writing that? Yeah, isn't it amazing? But we're not going to stop at a couple points. We want all the points. We're going to go all the way. And, okay, so how do we get all the way? Well, we need to start chipping away. So this is one of those things where, okay, series, we know what the answer is supposed to look like. Plug it in. Great. Now this uses, by the way, n as its subscript. Don't think too much about what letters being used as subscripts. It doesn't really matter because we can change it to be whatever we want it to be. If you prefer K's, just write them as K's. If you like N's, K, keep it as N's, or L's or P's, whatever. It's up to you. And so we'll start with N's because that's how they started here. We'll need some notes. We know that y prime, this is the sum, 0 to infinity of n, c sub n, x to the n minus 1, and y double prime is the sum from 0 to infinity n times n minus 1, cn x to the n minus 2. Okay, so y double prime, we copy it down, the sum, n equals 0 to infinity, n minus 1, cn x to the n minus 2, plus x minus 1 times y, which is the sum, n equals 0 to infinity, of c sub n x to the n equals 0. All right, there we go. We are on our way. And so just for those following along at home, remind ourselves what we've done. We put in y double prime, and we put in y. Now our goal is to mush these into one series. One series to rule them all. Okay, so, well, let's figure out how to do it. We have to do some distributing over here. Again, what's going on here is really this is a polynomial. A series is a huge, huge polynomial. And so when we have a polynomial times polynomial, which is what's going on here, this x minus 1 is polynomial. So polynomial times polynomial, we got to sort of combine, and the only way to do that is to multiply. So we're distributing through. And the easiest way, of course, is to distribute each term here, putting the sum in. Because then you just have to say, oh, I just have two pieces. A little bit easier than infinitely many pieces. Okay, so on our first one, looking ahead, we're going to do a shift down by 2. And we say, look, the first two terms don't matter, so we're going to go ahead and replace that by 2. So we have the sum from 2 to infinity, n minus 1, cn x to the n minus 2, plus, now when we have the x, we're going to multiply the x through, so that's the sum, n equals 0 to infinity of cn x to the n plus 1, excuse me, minus the sum, n equals 0 to infinity of cn x to the n. So this is the minus 1. And that equals 0. And now we go through term by term and say, okay, are we happy? Well, we need to check our powers. Do our powers align? If not, we fix that. Well, they don't. They're off. There's no consistency. So we just start. Now, this last one is easiest. We're pretty happy with that one, as is, actually. So we'll just do a substitution, L equals n. Here, we'll do a substitution, L equals n plus 1, or we could say n equals L minus 1. And of course, each one of these is a separate sum, so it's okay to say L equals n here, but L equals n plus 1 there, because they're their own little sandbox right now. So we're just playing with them individually. And what we do to one right now doesn't interact with what we do to another. They won't interact until we mush them together. And we're really trying to get them so that they can mush together. All right, this last one, we'll let L equal n minus 2, or that's the same as saying n equals L plus 2. All right, well, with that, we have now the following. The first sum, well, we started at n equals 2, L equals n minus 2, so now we start at 0. 0 to infinity. That's why we anticipated, by the way. See that 2, we said, oh, we're going to shift down by 2. So let's replace 0 by 2 because the first two terms don't matter. We'll have L plus 2, which is n, and L plus 1, which is n minus 1. We'll have C sub L plus 2, and then we'll have x to the L. That's our first sum. Our second sum. Well, we start at n equals 0. Well, where does L start? L equals n plus 1. So we really start at L equals 1. We go to infinity. Then it's C sub L minus 1, x to the L. Then our last one, well, this is the easiest one. It's the sum. All we're doing is we're changing our n's to l's. And there we go. Now are we ready to mush? No, because while our powers agree, our starts do not. So we're going to pull off the starts. And namely, we need to pull off the 0 here and the 0 there. So let's see what happens when we pull off our 0 terms. Going to move this up a little bit as we keep looking for more space. So when we pull off 0, we're going to get 2 times 1 times C2. So that's 2C2. Don't pull off anything. Here we pull off the 0 term. Subtract C0. Okay. Now, everything else starts at 1 after we pull off the first term. So we can put them all together into one sum. One sum. equal them all. Okay, we have L plus 2 times L plus 1, C sub L plus 2, plus C sub L minus 1 minus C sub L, and that's times x to the L, and all that equals 0. Okay, so we kind of did two steps at once. In some sense, the shifting is the hard step to do. So that's why I like to separate that, make sure we have that done. So what were our two things we did? We pulled off the L equals 0. So this is our, again for notes, L equals 0. And then we said, okay, everything else goes into the common expression. Now, what's going to happen? Well, the reason that we've done all of this is we now have polynomial equals polynomial, which means coefficients equals coefficients. Well, that means that this first coefficient equals 0, but also each one of these equals 0. All right, so let's make ourselves a list. I'm going to just remind ourselves that we already know that C0 and C1 are both 1. Okay, so our list here, we're going to form on the side C0 equals 1, C1 equals 1. We need to find C2, C3, and C4. And once we do that, we'll be done. So, come here. What does this say? 2C2 has to equal C0. Well, that says, look, we know C0 is 1, and 2 times something equals 1. So that says, hey, C2 has to be 1/2. So there we go. Now, there's a philosophy in play here, and I want to say this out loud so that you never can say, oh, Steve never said that out loud. The initial conditions prime the pump. So they give us the first one, and if it's a first order differential equation, or first two if it's a second order differential equation. Or, if it was higher order, but we wouldn't do that to you. We're friends. Yeah, of course we're friends. Okay, so we prime the pump, and now every time that we get the next coefficient gives us our next term. So we keep looking at coefficients. So this came from the L equals 0. We're going to look at L equals 1, and then we're going to look at L equals 2. And that's going to give us our pieces. All right, so again, I'll make that clear. L equals 0. And now, what do? Well, we're going to swap. Say, all right, what about L equals 1? Okay, come to here. 1 plus 2 is 3. 1 plus 1 is 2. 3 times 2 is 6. C3 plus, now, CL minus 1 is C0. And now subtract C1. And that equals 0. But wait, C0 is 1. C1 is 0. Those cancel. So we really have 6C3 equals 0. That says, hey, C3 equals 0. Cool. Well, that wasn't bad. And that leaves us with just one more to go. One last coefficient to solve for. L equals 2. 4 times 3 is 12. So 12 and 2 plus 2, C4. Plus 2 minus 1 makes C1. Minus C2 equals 0. Well, let's be careful here. So we can also say, oh, this says that 12C4 is equal to C2, which is 1/2, minus C1, which is minus 1, which is minus a half. So what's C4? So C4 is minus 1 over 24, right? Because we divide by 12. And that's it. That's it, right? Because it said, find the first 5 coefficients, C0, C1, C2, C3, C4. And there they are. So it's nice to just review what went on here. We started with, we knew our solution had to look like a series. We found what the derivatives look like. We plugged them into our original equation. So y double prime, x minus 1, y equals 0. We have our initial conditions, which is going to prime our pump. But in the meantime, we work on rewriting our series so we can combine them. First, making sure the powers line up, and then pulling off some starts so that we can put everything else into a single series. Really, we're grouping coefficients. That's what's going on. Now that we've grouped coefficients, we say, look, we got our start. Then each coefficient, as we move down, gives us our next term. So the constant term gave us our next piece. The coefficient of x gave us our next piece. And the coefficient of x squared gave us the last piece that we needed. And life was good. Life was wonderful. Well, all right, that was good. Make sure you're ready. Test is going to be fun. And I hope you enjoy it as much as one can. All right. See you later. Bye.